Welcome back. In this video, we will look at example problems of solving trigonometric integrals. Let's get to it. All right, so here's our first example. We have the integral of sine squared x dx. And so in order to solve this trigonometric integral, we are going to need to make use of a trigonometric identity. And so over here, I have some identities for sine and cosine that are going to be helpful in solving these various trigonometric integrals. And so we have the Pythagorean identities and the half-angle identities that we will use in different scenarios. Now in this case, in order to solve this integral, we are going to want to make sine squared x simpler. In other words, we are going to want to rewrite this to have a trig function to the first power rather than to a second power like we have here. And so instead of rewriting sine squared x with a Pythagorean identity, where we'd have 1 minus cosine squared x, which is still a squared trig function, it's going to be better to use the half-angle identity for sine squared x, which is equal to 1/2 times 1 minus cosine of 2x, which is easily integrated since it's cosine to the power of 1. And so if we do that, if we use that half-angle identity, we'll have that this is equal to the integral of 1/2 times 1 minus cosine of 2x dx. Okay? And so if we pull that 1/2 to the outside of the integral, this will be equal to 1/2 times the integral of 1 minus cosine of 2x dx. And now what we can do is split up this integral into two integrals. We'll have 1/2 times the integral of 1, and then subtract 1/2 times the integral of cosine of 2x. And so I'll do that. We'll write that this is equal to 1/2 times the integral of 1 times dx minus 1/2 times the integral of cosine of 2x dx. Okay, and so if I clean up my work here, we know that the integral of 1 is just going to be x because 1 is a constant, and the integral of a constant is just going to be equal to the variable of integration. And so this will be equal to 1/2 times x, and then we will subtract 1/2 times the integral of cosine of 2x, which we can integrate using u-substitution since we have a composite function, right? We can set u equal to 2x and then take the derivative of that. So we'll have du dx is equal to 2 because the derivative of x to the first power is just equal to its coefficient, which is 2. And so du is equal to 2 times dx if we solve for du by multiplying both sides by dx. And then whatever du is equal to, we want to be able to find within our integral. Now I see dx right here, but I don't see a 2, and so I'm going to divide both sides by 2, and we'll have du divided by 2 is equal to dx. And now we can rewrite this integral in terms of u, so we'll have cosine of u times du divided by 2. Right, we replaced 2x with u because that's what we set it equal to, and we replaced dx with du divided by 2 because that's what we found that was equal to. And so now, if we pull this 1/2 to the outside of the integral, this is equal to 1/2 times x minus 1/4, because 1/2 times 1/2 is 1/4, times the integral of cosine of u, and that's multiplied by du, and the integral of cosine is just equal to positive sine, and so we'll have that this is equal to 1/2 times x minus 1/4 times sine of u plus c. And now all we have to do to find our final answer is replace u with what we set it equal to, which is 2x. And so if I rewrite that, we will have sine of 2x plus c. And that will be the solution to this trigonometric integral. Let's look at another example. So here's our next example. We want to integrate cosine cubed of x times dx. All right, so now in this case, our cosine function has an odd power, right? 3 is an odd number, and so cosine is raised to that power of 3, and when you have an odd power for a trig function, you should try and split that up so that we can use one of our identities to make this integral solvable. So if we do that, let's split cosine cubed of x to be cosine times cosine squared, so this will be equal to the integral of cosine x times cosine squared x dx. And now we can rewrite this cosine squared x with one of our identities. Now generally, when you split up a trig function with an odd power, you are then going to want to rewrite the squared part with a Pythagorean identity. All right, we usually leave the half angle identities for when we have an even power in our original integral. And you saw that with our previous example. And so in this case, we are going to use the Pythagorean identity for cosine squared x to rewrite this part of our integral. And so if we change that to be 1 minus sine squared x, we will have that this is equal to the integral of cosine x times 1 minus sine squared x times dx. Now the reason we do that is because now we can use u-substitution and the power rule of integration to solve this integral, right? Because if we set u equal to sine x, then we could rewrite sine squared x as u squared, because sine squared x is just sine squared, and so sine squared x will be u squared. And then if we take the derivative of u, du dx will be equal to the derivative of sine, which is cosine x, and so du will be equal to cosine x dx, and whatever du is equal to, we need to be able to find that within our integral, and cosine x dx is right there. And so rewriting our integral in this way allows us to use u-substitution and simplify this integral and make it solvable. And so generally, when you use your Pythagorean identities with sine and cosine to simplify an integral to be solvable, you're going to want to set u equal to the trig function that is inside that identity that you used, right? So in this case, we switched cosine squared x to be 1 minus sine squared x, which means that we're probably going to want to set u equal to sine, all right? And that's what we did in this case, and that's going to allow us to solve this integral. And so if we rewrite it in terms of u, it will be equal to the integral of 1 minus u squared times du. Okay, so we replaced sine squared x with u squared, because u is equal to sine, so sine squared is u squared. And then we replaced cosine x dx with du, because that's what we found that that was equal to. And now we have a fairly simple integral that we can solve by using the power rule of integration. And so if I clean up my work here, let's integrate each of these terms. The integral of 1 will be equal to u, because the integral of a constant is equal to that constant times the variable of integration, which in this case is u. And then we will subtract the integral of u squared, which if we use the power rule, we will have u to the third power divided by 3, right? We add 1 to the exponent and then divide by that new exponent. And then of course, because we are integrating an indefinite integral, don't forget to add plus c. And then all we have to do now to finalize our answer is replace u with what we set it equal to, which is sine x. And so our final answer is that this is equal to sine x minus sine cubed x divided by 3 plus c. And that is the solution to this trig integral. All right, so here's our next example. We have the integral of sine to the third power of x times cosine to the fourth power of x dx. And so in this case, we have a trig integral with both sine and cosine in the integrand. And so what we want to do here is look at the powers of sine and cosine and see if we have any odd powers. And if we do, we want to split that odd power up. And so in this case, sine is to the power of 3, which is an odd number, and cosine is to the power of 4, which is even. And so in this case, we want to split up sine cubed x to be sine times sine squared, which will allow us to use one of our identities. And so let's do that. This will be equal to the integral of sine x times sine squared x times cosine to the fourth power of x dx. Okay? And so now that we split up an odd power, we want to rewrite the squared term with one of our Pythagorean identities. In this case, we have sine squared x, so we will rewrite sine squared x with 1 minus cosine squared x. And so this will be equal to the integral of sine x times 1 minus cosine squared x multiplied by cosine to the fourth power of x times dx. And now that we have rewritten sine squared x to be 1 minus cosine squared x, we can use u-substitution to solve this integral. And so like I said in the previous example, whatever trig function shows up in what you replace your squared function with using your identity, that's going to be the trig function you want to set equal to u. And that will generally be the case for integrals with sine and cosine. And so if we do that, u will be equal to cosine x, and the derivative, du dx, will be equal to negative sine x, right? The derivative of cosine is negative sine. And then from that, du will be equal to negative sine x times dx. And so then whatever du is equal to needs to be found within our integral. And so I see a sine x and a dx, but I don't see a negative sign. And so I'm going to multiply both sides by -1, and we'll have negative du is equal to sine x dx. And now we can replace sine x dx in our integral with negative du. Okay, so we can replace cosine squared x with u squared, since u is equal to cosine. So cosine squared will be u squared. And then cosine to the fourth power of x with u to the fourth power. And then sine x dx will become negative du. And so if we rewrite our integral in terms of u, this is equal to the integral of 1 minus u squared times u to the fourth power times negative du. All right, and so if I clean up my work here, we can simplify what we have here by pulling this negative out to the front and then distributing u to the fourth power through this quantity. And so this will be equal to the negative integral of u to the fourth power minus u to the sixth power times du. And then I'm going to distribute that negative through these two terms now. So we'll have that this is equal to the integral of negative u to the fourth power plus u to the sixth power times du. And now we can integrate each of these terms using the power rule of integration. And so if we add one to their exponents and divide by that new exponent, we'll have that this is equal to negative u to the fifth power divided by 5 plus u to the seventh power divided by 7, and then plus c. Okay? And so then all we have to do to finalize our solution is replace u with what we set it equal to, which is cosine x. And so if I clean up my work one more time, we will have that this is equal to negative cosine to the fifth power of x divided by 5 plus cosine to the seventh power of x divided by 7 plus c. And so that is the solution to this trigonometric integral. All right, so for our next example, we have the integral of cosine to the fourth power of 5x dx. Okay, so in this case, we just have cosine in our integral, but it's raised to a fourth power, which is an even power, and so we don't need to split anything up here. Rather, we should rewrite this using one of our half-angle identities. Typically, you will use your half-angle identities when you have sine or cosine to an even power, and they're by themselves in the integral, or you have sine times cosine and both have an even power. All right, so in general, you want to simplify an even power using a half-angle identity. And so in this case, we're working with cosine, and we know that cosine squared x is equal to 1/2 times 1 plus cosine of 2x. And so we could rewrite this integral to be equal to the integral of cosine squared of 5x squared times dx, right? Cosine squared of 5x squared would be cosine to the fourth power of 5x. And so we can rewrite this cosine squared of 5x using this half-angle identity. Just remember that the angle of cosine squared will be doubled when we write out cosine of 2x, right? So in this case, we have cosine squared of 5x. That 5x is going to be multiplied by 2 when we rewrite this cosine function using this half-angle identity. And so what we'll have is that this is equal to the integral of 1/2 times 1 plus cosine of 2 times 5x squared times dx. Okay, and so if we square both parts here, we will have that this is equal to the integral of 1/4 times 1 plus cosine of 10x, right? 2 times 5 is 10, and that will be squared times dx. Okay, so 1/2 squared is 1/4, and then we squared this quantity, and so we have 1 plus cosine of 10x squared. All right, and so if I clean up my work here, we can simplify this by pulling this 1/4 to the outside of the integral and then expanding this squared quantity, right? So this will be equal to 1/4 times the integral of the expansion of this squared quantity. And so I'm going to use a trick here. We will square the first term, then multiply the two terms together, and then multiply them by 2, and then square the last term, right? So we'll have 1 squared, which is just 1, and then we will add these two terms multiplied together and then multiplied by 2. And so cosine of 10x times 1 is cosine of 10x. And so if you multiply that by 2, our middle term will be 2 times cosine of 10x. And then our last term, we will add the second term in our quantity squared. So we'll square cosine of 10x, and we will have cosine squared of 10x. All right, and that's multiplied by dx. And so now we can split this integral into 3 integrals so that we can focus on each of these terms individually. So if we do that, we will have that this is equal to 1/4 times the integral of our first term, which is 1, so we'll have 1 dx, plus 1/4 times the integral of our second term, which is 2 times cosine of 10x dx, and then we will add 1/4 times the integral of our last term, which is cosine squared of 10x, and so I'll have cosine squared of 10x dx. Okay? And so if I clean up my work here, we can now focus on solving each of these integrals individually. And so let's start with our first one. We know that the integral of 1 is just going to be x because the integral of a constant is that constant times the variable of integration. And in this case, that variable is x. So 1 times x is x. So this is equal to 1/4 times x. And then we will add that to this integral. Now, if you pull that 2 to the outside, 2 times 1/4 is 1/2. So we'll have 1/2 times the integral of cosine of 10x times dx. And we could solve this integral using u-substitution, but we'll come back to that. And we will add our last integral, which is 1/4 times the integral of cosine squared times 10x dx. And we will solve this integral by using another half angle identity. Right, we have cosine squared of 10x, which is another even power, and we can't easily integrate cosine squared otherwise, and so we need to simplify that and rewrite it using a half angle identity. Okay, and so before we do that, let's rewrite our first term, and then let's start solving this integral using u-substitution. This will be equal to 1/4 times x plus 1/2 times the integral of cosine of 10x dx. Now we can set u equal to 10x, since that is the inside function of cosine. And so if we do that, I'm going to write that up here. We'll have u is equal to 10x, which means that du dx is equal to 10, because the derivative of 10x is 10, which means that du is equal to 10 times dx, but I don't see a 10 within our integral, and so if I divide both sides by 10, we will have that du divided by 10 is equal to dx. And now we have a term of du that can replace something that we can find in our integral, which is dx. Okay, so if we rewrite this integral in terms of u, we will have cosine of u times du divided by 10, and then we can continue on with our next integral. So we will add that to 1 divided by 4 times the integral of cosine squared of 10x, but we're going to rewrite that using the half angle identity for cosine squared. Just remember, once again, that angle of 10x is going to be doubled when we write out that new cosine function because we have cosine of 2x. Okay, so we'll rewrite this cosine squared function using that half angle identity, and we'll have 1/2 times 1 plus cosine of 2 times 10x, and that will be multiplied by dx. All right, and so if we simplify, this will be equal to 1/4 times x plus this integral, and we can pull out this 1/10 to the front and multiply it by 1/2, and we'll have 1/20 times the integral of cosine u du, and then we'll integrate that. But first, let's rewrite this integral. This will be added to 1/4 times 1/2 if we pull that 1/2 out front, and so we have 1/8 times the integral of 1 plus cosine of 20x times dx, right? 2 times 10 is 20. Okay, and so if I clean up my work here, we can integrate this integral because we know that the integral of cosine of u will be sine of u, and so this is equal to 1/4 times x plus 1 divided by 20 times sine of u, and then we will add this integral, and I'm going to actually split this up into 2 integrals. We'll have one integral for each of these terms. We'll have 1 divided by 8 times the integral of 1 plus 1 divided by 8 times the integral of cosine of 20x. So I'll write that. We have 1/8 times the integral of 1 dx plus 1/8 times the integral of cosine of 20x dx. Okay, and now if we replace this u for sine of u with what we set it equal to, which was 10x, this is equal to 1/4 times x plus 1 divided by 20 times sine of 10x. So now that is a completed term of our solution. And we will add that to 1/8 times the integral of 1. And remember, the integral of 1 is just x. So we have 1/8 times x. That is another completed term of our solution. And we will add that to this integral, which similar to what we had before. Remember, for this term, we had cosine of 10x, and we used u-substitution to solve that. We could do the same thing here, right? We can set u equal to 20x and then solve that integral. But we already used u previously, and so if you're following along and writing down all of this work, you don't want to use u twice to avoid any confusion. And so while I'm going to erase this, and it really wouldn't matter for me, I'm going to use the variable w so that you don't get confused in your work. All right, so w will be equal to 20 times x, which means that the derivative, dw dx, will be equal to 20, right? The derivative of 20x is 20, which means that dw is equal to 20 times dx. And we want to find whatever dw is equal to within our integral. But I don't see 20 dx, I just see dx. So we'll divide both sides by 20, and we'll have that dw divided by 20 is equal to dx. Okay, so now we can rewrite this integral in terms of u, or in this case, in terms of w. And so we'll have 1/8 times the integral of cosine of w times dw divided by 20. And now we can simplify. Note that we have 1/4 x and 1/8 x. Those can actually combine. They are like terms, and 1/4 is the same as 2/8. And so 2/8 plus 1/8 is 3/8. So this is equal to 3/8 times x plus 1 divided by 20 times sine of 10x plus this integral, which we can simplify by pulling 1/20th out to the front. So we have 1/8 times 1/20th, which is 1 divided by 160. So we have 1 divided by 160 times the integral of cosine of w times dw. All right, and so if I clean up my work one more time, we know that the integral of cosine is going to be sine, and so this is equal to 3/8 times x plus 1 divided by 20 times sine of 10x plus 1 divided by 160 times sine of w plus c. And remember that w is equal to 20x, and so if I rewrite this, we'll have sine of 20x plus c, and that is the final answer to this trigonometric integral. Okay, so that was a lot of work because we had a lot of terms that resulted from using our half-angle identity, but in the end, we were able to find the solution to this integral that otherwise we wouldn't be able to integrate without the half-angle identity. Okay, let's look at a different example. All right, so here's our next example. We are now going to be looking at trig integrals that involve tangent and secant. And so when you have integrals with those two functions in them, we only have two trig identities to work with. We have two Pythagorean identities, one for secant squared x and one for tangent squared x. Okay, so similar to sine and cosine integrals, when you see tangent and secant, you want to be on the lookout for odd powers. And when you see that, you should almost always split them up. The only exception to that is if you have tangent to an odd power and then you have secant squared x, because you could just use u-substitution right away since the derivative of tangent is secant squared. And I have an example of that in my lesson video on this topic if you want to check that out. All right, but in this case we have two odd powers, and so let's split them up. We're going to rewrite this integral to be tangent x times tangent squared x times secant x times secant squared x dx. Okay, so I split each of these trig functions to be that trig function to the first power times that trig function to the second power, or times that trig function squared. All right, and then in most cases, when you split an odd power in an integral with tangent and secant, you're going to want to solve that integral with u-substitution and set u equal to secant. But before we can do that, we need to rewrite tangent squared x with our Pythagorean identity for that function. And so if I do that, watch what happens. This will be equal to the integral of tangent x times tangent squared x, which is equal to secant squared x minus 1. So we'll have secant squared x minus 1 times secant x times secant squared x dx. And now what we can do is we can use u-substitution and set u equal to secant, and we will be able to rewrite this integral in terms of u, which will make it solvable, right? So if we do that, u is equal to secant x, then du dx is equal to the derivative of secant, which is secant x tangent x. And that means that du is equal to secant x tangent x dx. And so if you look at our integral here, if we set u equal to secant x, we can rewrite this secant squared x to be u squared, and this secant squared x to be u squared, and then du can replace secant x tangent x dx, which can be found here. Here's our tangent x. Here's our secant x, and here is our dx. All right, so these three parts are going to be replaced by du, and then secant squared x and secant squared x will be replaced with u, or more specifically, u squared. And so if we rewrite our integral, this will be equal to the integral of u squared minus 1 times u squared times du. Okay, so these three parts were replaced with du because that's what it's set equal to, and secant squared x turned into u squared in both places because we set u equal to secant x. And now if I clean up my work here, we can distribute u squared through this quantity, and then we'll be able to integrate using the power rule of integration. And so this is equal to the integral of u to the fourth power minus u squared times du. And now if we use the power rule, we'll add 1 to each exponent and divide by that new exponent. And so this is equal to u to the fifth power divided by 5 minus u to the third power divided by 3 plus c. And so now, if we replace u with what we set it equal to, we will have our final answer. And so this is equal to secant to the fifth power of x divided by 5 minus secant to the third power of x divided by 3 plus c. And so that is the solution to this trigonometric integral. Let's look at another example. All right, so here's our next example. We have the integral of tangent to the fourth power of x dx. And now for this integral, in its current state, we obviously can't integrate it using any of the techniques that we know, so we need to simplify it a little bit or manipulate it using a Pythagorean identity. And so we know that tangent squared x is equal to secant squared x minus 1, and so we can rewrite tangent to the fourth power of x to look like this. This is equal to the integral of tangent squared x squared times dx, right? If you square tangent squared, you'll have tangent to the fourth power. And so if we replace tangent squared x with the identity of secant squared x minus 1, then we'll have that this is equal to the integral of secant squared x minus 1 squared dx. All right, and so now what we can do is expand this quantity that is squared, and we'll have three different terms that we can then integrate individually. And so I'm going to use a little trick here again to square this quantity quickly. We will square the first term, then add the two terms multiplied together, then multiplied by 2, and then add the last term squared. So this will be equal to the integral of secant squared x squared, which will be secant to the fourth power of x, and then we will add these two terms multiplied together times 2. So secant squared x times negative 1 is negative secant squared x times 2 will be negative 2 times secant squared x, and then we will add our last term squared, and negative 1 squared is positive 1. And so that will be multiplied by dx. Okay, and so now just like I said, we have three terms here that we are integrating, and so I'm going to split them up into three separate integrals. And so this will be equal to the integral of secant to the fourth power of x dx minus the integral of 2 times secant squared x dx plus the integral of 1 dx. Okay, and so if I clean up my work here, we can now work on integrating each of these integrals individually. And so let's start with our first integral here. We have the integral of secant to the fourth power of x dx, and we currently don't know how to integrate that in its current state. And so let's split it up. We will rewrite it to be equal to the integral of secant squared x times secant squared x dx. That will allow us to use our Pythagorean identity for secant squared x. I'm not going to replace both of them with that identity. I'm just going to replace one. And I'll tell you why when we get back to this integral, but let's work on simplifying these two over here. If we pull this 2 out to the front, we'll have minus 2 times the integral of secant squared x dx. All right, and then for this integral, you might be tempted to use a Pythagorean identity to change secant squared x to 1 plus tangent squared x, but we actually don't need to do that in this case because we actually know what the integral of secant squared x is. It's just tangent, right? The derivative of tangent is secant squared x, and so the integral, which is the opposite of taking the derivative of secant squared x, will give us back tangent. And so we'll do that when we get back to that integral in our next line. But then for our last integral here, the integral of 1 dx is just going to be x. And so we'll add x, and then just so we don't forget it later, I'm going to add c. All right, and so now let's rewrite one of these secant squared x's in this integral with that Pythagorean identity. And so this will be equal to the integral of 1 plus tangent squared x times secant squared x dx. And the reason we only change one of them is because that will allow us to use u-substitution here, right? If we set u equal to tangent, the derivative of tangent, like I said earlier, is secant squared x. And so u-substitution is going to work for this integral. And so we'll come back to that. Remember that I said we can integrate secant squared x to be tangent. So we'll have minus 2 times tangent x, and then we will add x plus c. And now all we have left to solve is this integral. And so if I clean up my work, let's use u-substitution on this integral. We'll have that u is equal to tangent x, which means that du dx, the derivative of u, will be equal to secant squared x, and that means that du will be equal to secant squared x dx. And so du will replace this right here, secant squared x dx, and u will replace tangent squared x, and we'll have u squared instead. And so this will be equal to the integral of 1 plus u squared times du. And then I'll write the rest of our terms here. We have minus 2 times tangent x plus c. And now we have two terms here that can be easily integrated. And so the integral of 1 is u, so this is equal to u, plus the integral of u squared, which if we use the power rule for integration, by adding 1 to the exponent and dividing by that exponent, we'll have u cubed divided by 3, and then minus 2 times tangent x plus c. And now, to get our final answer, we just have to replace u with what we set it equal to, which is tangent. And so this is equal to tangent x plus tangent cubed x divided by 3 minus 2 times tangent x plus c. Now this would be our final answer, but we can actually simplify one more thing. Note that we have like terms of tangent x and negative 2 times tangent x. And so if we add 1 tangent x to negative 2 tangent x, this will become negative 1 tangent x. And so if I clean up my work one more time, we will have for our final answer that this is equal to tangent cubed x divided by 3 minus 1 tangent x plus c. All right, and so that is the final solution to this trig integral. Let's look at one more example for this video. All right, so here's our last example. We have the integral of tangent cubed x divided by secant squared x times dx. And so in this case, if we look at both of our trig functions, we have tangent to the third power and secant squared. And so since we have tangent to a power of 3, which is odd, we should start by splitting up that odd power. And so this will be equal to the integral of tangent x times tangent squared x divided by secant squared x dx. Okay, and so now that we split up that odd power, let's use a Pythagorean identity to replace tangent squared x here. So we'll rewrite that to be secant squared x minus 1. And so this will be equal to the integral of tangent x times secant squared x minus 1 divided by secant squared x times dx. All right, and so now that we've done that, we should try and use u-substitution to solve this integral. And so if we set u equal to secant x, this denominator would become u squared, and this secant squared x would also become u squared, but the derivative of secant isn't entirely found within this integral, right? Du dx would be equal to secant x times tangent x, which means that du is equal to secant x times tangent x dx. And so we're missing a secant function in the numerator to be multiplied by tangent x in order to rewrite this integral in terms of u. But we can actually get around this by introducing another secant function, right? What we can do is multiply this integral by a form of 1, which doesn't really change the function. And that form of 1 will be secant x divided by itself, right? Anything divided by itself is 1, and so secant x divided by secant x is just 1. And so we're going to multiply our integral by that form of 1, and that will introduce another secant in the numerator that we can then replace du with, and it will just increase our denominator by a power of 1. And so instead of having u squared in the denominator, when we rewrite this in terms of u, we'll have u to the third power instead. And that's not a big deal. And so if I clean up my work here, we can rewrite this integral to be equal to the integral of tangent x times secant x, right? That secant x comes from right here, and that will be multiplied by secant squared x minus 1 divided by secant to the third power of x dx. And now we can rewrite this integral in terms of u. And so if we do that, this will be equal to the integral of u squared minus 1 divided by u cubed times du. Right? We replaced secant squared x with u squared. We replaced secant cubed x with u to the third power. And then we replaced tangent x secant x times dx with du because that's what we found that was equal to. Okay, and so if I clean up my work here again, we can now work on solving this integral. And so in order to do that, I'm going to split up the numerator and divide each term by the denominator. So this will be equal to the integral of u squared divided by u cubed minus 1 divided by u cubed, and that's multiplied by du. And so by doing that, this u squared divided by u cubed will just become 1 divided by u, because 2 of these u's will cancel out with 2 of these, and so we're just left with u to the first power in the denominator. And so this is equal to the integral of 1 divided by u minus 1 divided by u cubed times du. And that can be rewritten to be equal to the integral of u to the negative first power minus u to the negative third power times du. And now we have two terms that we can integrate pretty easily to find the solution to this integral. And so I'll clean up my work, and we can integrate each of these terms. Now be careful, you can't use the power rule of integration on u to the negative first power, because if you add 1 to the exponent, negative 1 plus 1 is 0, which means you'd be dividing by 0, and that's undefined. And so instead of using the power rule of integration, remember that the integral of u to the negative first power, or 1 divided by u, will be the natural log of the absolute value of u. Right, the integral of 1 divided by x times dx is equal to the natural log of the absolute value of x, and so the integral of 1 divided by u, or u to the negative first power, times du is equal to the natural log of the absolute value of u. Okay, and so that's what we'll have for that first term. This will be equal to the natural log of the absolute value of u, and then we will subtract the integral of u to the negative third power, which we can use the power rule of integration for. So we'll add 1 to that exponent to have u to the negative second power, and then divide by that new exponent of negative 2. And then don't forget to add plus c. And so if we simplify, these negatives will cancel out, and then we can move this negative exponent back to the denominator by making it positive. And so this is equal to the natural log of the absolute value of u plus 1 divided by 2 times u squared plus c. Okay, and then we can finalize our answer by replacing u with what we set it equal to, which is secant x. And so if we do that, we'll have that this is equal to the natural log of the absolute value of secant x plus 1 divided by 2 times secant squared x plus c. Now you could say that this is your final answer, but we can actually simplify it a little bit more yet, because we know that 1 divided by secant is equal to cosine, and so 1 divided by secant squared x will be equal to cosine squared x. Okay, so if I clean up my work here, since we know that 1 divided by secant squared x is the same as cosine squared x, we'll have that this is equal to the natural log of the absolute value of secant x plus 1/2 times cosine squared x plus c. Right, I just pulled that 1/2 to the outside from that trig function, so that when we changed it to cosine squared x, we have 1/2 times cosine squared x. All right, this is the final answer to this trigonometric integral. And so with that, this was the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.